Got another exam question on the acids, bases and pH topic. So this one's number 6. As always, the link to the questions in the description. Just click on that, have a go at the question and then play on for the answers. First part of A, what's meant by the term Bronsted-Lowry acid? So all you need to say is it's a proton donor. You could put H plus donor there if you wanted to. What's meant by the strength of an acid? So acid strength is linked to the extent of dissociation. So I'm just saying something like this: the stronger the acid, the greater the extent of dissociation. And I'm just going to illustrate that with the first one from the table. Obviously you could have done that for any of the acids in the table, but I've gone for the first one. And the next part, we've got to order the acids using their pKa values from weakest to strongest. So just like pH, the lower the pH number, the stronger the acid. Likewise for pKa, the lower the pKa value, the stronger the acid. So the order is that. And the last part of it, all we've got to do is complete the equation. We don't have to identify the acid-base pairs. Sometimes you get asked to do that. So what we've got to do is look at the pKa values of the two acids in question. So benzoic acid 4.19 versus lactic acid 3.86. So that lower pKa value for lactic acid means it's a stronger acid. So it will therefore donate its proton to the benzoic acid, which is meaning that the benzoic acid has to act as a base, which gives us those. Moving on to part B, so we've got to write a full equation and then an ionic equation for this reaction between pyruvic acid and aqueous calcium hydroxide. So basically acid plus, this is an alkali, we're going to get salt and water. The formula of calcium hydroxide is CaOH twice, so they're kind of testing you on your knowledge of that. So there's the reaction equation there. Moving on to the ionic equation now, so we've got in the acid, we've got 2 of these negative ions here and 2 H plus ions. In the calcium hydroxide aqueous, we've got a Ca2 plus aqueous and 2 hydroxide ions. Moving on to the products, we've got 2 aqueous, these negative ions that we saw in there, so they're obviously going to cancel. We've got an aqueous Ca2 plus ion, which is going to cancel with that one, and we're making 2 lots of water. So the ionic equation simplifies right down to that. Moving on to calculation, I've already written up the equation that we use, the formula we use to calculate the H plus concentration of a weak acid, because we've got to get the pH of this. So I call it the square root of Ka, just as a way to remember it. So what do we need to know? We need to know the Ka value. Well, we can get that from the pKa value. And the HA is the original concentration of the acid. Well, we've got that in the question. So we'll go through the numbers now. So Ka is 10 to the minus pKa, so 4.07 times 10 to the minus 3. Don't worry about the units, but that's what they are. The H plus concentration, therefore, the square root of Ka times the concentration of the acid. So it's that many moles per decimeter cubed. All we need to do now is minus log that, and we'll give the pH to 2 decimal places. So we'll get a pH of 2.11. Part D, the structure of oxalic acid is going to look like that. You could just put OH there if you wanted to, and there. And now the 2 equations that give rise to each dissociation. So basically, we're going to start with this. It's going to donate its first H plus, and then whatever's produced from that then loses the second H plus. So there's the first one, and there's the second one.